Okay, so here we're going to start investigating the question, really. Will repeated roots change the behavior of the graph at whatever that x-intercept is? So we'll start by thinking about, okay, what does the graph of x plus 5 look like? Well, we know that that has a y-intercept of 5 and a slope of 1, right? M equals 1 for this one, b equals 5. And so we can say, you know, it looks, let's see if I can do this. There we go. Well, can't quite draw a straight line, but you all get the idea, right? It looks pretty much like that. Domain, same, and this is a polynomial, even though it's a linear function, right? Domain, all real numbers. Long run behavior, we're going to say as x goes to negative infinity, y is going to negative infinity, and as x goes to positive infinity, y is going to positive infinity. And does it have any zeros? Why, yes, of course it does. X plus 5 equals 0, x equals negative 5, which is where we ran into the x-axis. Okay, great, we've got that. What's going to happen with x squared? Right? Now we know that that's a parabola, right? And we know basically that this is a parabola, just this is the graph of y equals x squared, but shifted 5 units to the left, right? We learned about that in chapter 3 when we talked about transformations, right? And so our normal parabola, let's see here, can I do this like, yeah, 9. So our normal parabola would look something like this, right? But we are going to move it 5 units to the left. So we've got these kind of points here. I don't even have to plug anything in. So it's going to look like this. Ooh, can't hit my points. There we go. Okay, so there's our graph. What's our domain? All real numbers. What's our long run behavior? We're going to say as x goes to negative infinity, y is going up, so positive infinity. And as x goes to positive infinity, y is going also to positive infinity. And do we have any zeros? Yes, we do. We can do that same x plus 5 equals 0. We've got a 0, just like we expected, at negative 5, which is what the transformation shift to the left told us. Okay, so what's the graph of x plus 5 cubed going to look like? So we're going to make the same argument, right? That this is the graph of y equals x cubed shifted 5 to the left, right? So our graph of x cubed normally would look like this, right? And we'll try to sketch that. And when we shift it 5 to the left, of course, all those points move over to 5 units. And we're here, and we're here. There we are. And so we've got this kind of graph going on, right? So there's not really anything, I mean, this is chapter 3 again, right? So what's our domain? All real numbers. What's our long run behavior? As x goes to negative infinity, y is going down, right? Y is going to negative infinity. And as x goes to positive infinity, y is going up to positive infinity, right? Okay, and do we have any zeros? Yes, we have, again, x plus 5 equals 0, x equals negative 5 for our 0, which is where we had it. Okay, so, and in fact, we can go do this with GeoGebra and kind of get an extreme idea here, which is what I'm going to do. We're going to go over to GeoGebra, and we're going to plot y equals x plus 5 to a power. And that's going to give me a slider. And I'm going to go put some restrictions on that slider because this is a polynomial. So the slider values are going to go from 1 to, let's say, 10. 10, min, max, there we go, 10, and increment of 1. There we go. Okay, so we've got, there's the first line that we graphed, right? Then we've got x squared, right? Then we've got x plus 5 to the third, and we see we get that cubic shape going on. And then x plus 5 to the fourth, we see it bounces, it doesn't cross the x-axis, but it is getting a little bit flatter than what it was at 2. And likewise with 5, it's crossing the x-axis, but now it has this S shape, and it's getting a little bit flatter. And if I go up to 6, I'm going to see, we know it's going to be a U shape, but we see it's not crossing the x-axis, it's getting a little flatter. 7, it is crossing the x-axis, getting flatter still, and so on and so forth, right? It just keeps getting flatter as the power keeps going up. So can we make a conjecture from that? What did we notice about the multiplicity of the zeros in the graphs? And if, you know, we were face to face, hopefully one of you would say, well, when the power of my root, when the multiplicity rather of my root was even, it didn't pass through the x-axis. And when it was odd, it did, right? So we can write that. So even multiplicity, there we go. We would say the graph does not cross the x-axis. It bounces, right? It kind of bounces off the x-axis. And if it is odd, it does. It crosses. Okay, so we've got this kind of summarized on the next slide, right? So the multiplicity of a 0 affects the behavior of the graph at that particular x-intercept. Now remember, at most, a polynomial function of degree n will have at most n zeros, right? So if we have a 0 multiplicity 1, it just straight up crosses the x-axis, like that, right? If it's a 0 with odd multiplicity, like 3 or 5 or 7, it's going to cross the x-axis, but we have a change in concavity, right? Like this part is concave up, right? And this part is concave down, right? Concave up, concave down. And if we have an even multiplicity, the graph is going to touch the x-axis, but not cross it. So we're going to end up with like this, right? There's our 0. And the higher the multiplicity gets, the flatter it gets right around that 0, because if we have a number less than 1 and we raise it to power, it gets even smaller. Okay, so that is a good place to break and go to the next video.